En de audio gaat ook goed, of gaat het gewoon via deze microfoon of zo?
Yes.
Oké.
Jij kan hem wel even openen.
Mag ik misschien deze? Ja.
Ja hoor.
Dan mag jij wel eens even lekker.
Okay, everybody ready? Alright, I'm going to talk about the assignment we do for ProRail. It's called digitaal schouwen in Dutch, but because I thought I'd translate it as you do a fleet review, you do a review of your assets in this case. We're doing this from SMART, and SMART is all about innovation, and this is specifically the track concerned with artificial intelligence and computer vision. So, I'll explain what it is first, why we're doing this, why ProRail wants this, and a little bit about how it works. Well, let's just get started. Oh, I have a thing. So this is basically the reason why ProRail wanted to have this system. In Stavoren in 2010, there was a big accident with this train. This was a driver that was unfamiliar with this trajectory, and there was a sign missing. So there was supposed to be a sign, lower your speed, and it was at night. The driver wasn't familiar, so the sign was missing. So he wouldn't have seen it. And this is what happens if you have, I don't know how much these trains weigh, but if they don't brake, this is how they brake, if they reach the end of the track. So, because this was such a silly mistake, right? The thing was missing. How can this happen? So, ProRail said, never again. So, we're going to sort of... that's the wrong way. So, the digital review is sort of two parts. We call this inside and outside. The inside is like the plans. So this is what you call the OBE sheets. Those are schematics. I'll show what they look like in a minute. And they sort of record how everything was designed, how it should be. And then there's the outside world, and that is how it is actually made. Usually, if there's a discrepancy, the outside world is wrong. Because the inside world, the designs, the schematics, they're designed like that for a reason. So if there's a discrepancy, you can do one of two things: change the plan or dig out that sign, put it somewhere else. So now, of course, the first thing is maintenance, because there's a whole lot of track that we don't know what shape they are in. But if there's a new trajectory, new construction, then you can do a review before you even take it into use. So those are the goals. Right, so the application, broadly speaking, looks like this. We have the schematics over here. They're in a digital format right now, so but we still have to interpret them. Then there's the outside world, which is images and GPS. And we bring them together in this interface where you have the schematics, the video, and also a list of everything that should have been there, and the state that it's in. So I'll talk about the inside world a little bit, and I'll mostly talk about the outside world because this is what is typical for the Smart AI computer vision group. So I know most about this, but if there are questions about any of the other sections, I can answer them as well. So these OBE sheets, this is what they used to look like. They're huge drawings. Bigger than this screen over here. They used to be done by hand, but luckily we have advanced. So now they are digital, but they are still schematic. Of course, they need to be schematic because things like these switches. What's most important is where are they, and where are the signs located. And this line right here could be 500 kilometers, and this is probably a meter or so. So they're not geographically correct. So if you want to know where, for instance, this sign over here, where it really is, then you have to translate it. There's another system, it's called BBK, basisbeheerkaart, and it has the same information. Well, actually, it doesn't have the same information. It has some of that information geographically correct. So what you now need to do is use these two systems, the ODE sheets and this BBK system, and sort of place all these designed objects in their correct spot. So this is the BBK excerpt. This is the same thing in ODE. And so some features you can recognize easily. So this is that switch that where these two tracks come together. So that's right about here. And then there's another track down there, which is this one. Here also is parts of the station which are not on this one, I think, or maybe they're there. I don't know. Wrong line. Right. Oh, the brown line. Oh, right. There you go. Okay. So they have some of this information. Now, what you see here as well, these numbers, those are the kilometer tape measure. So those are a system to know where on this track are we. And you can see those here as well. Well, actually, you probably can't see because it's too small, but here at the top you see these horizontal rulers, and they have the same information. The thing is, this track and this track might be on a different system. Challenges that our team had to solve. So if I want to know this triangle right here, this is a sign. If I want to know what is its correct position, then I have to know which of these tape measures does it belong to. Then I have to go to this other system, look it up, and see. Okay, well then I only know where it is on this line, but then you have to project it to there or there. So already you're in a bit of a pickle because there's a lot of information that you need to gather and interpret correctly. But once you have done all that, then you have your inside information. This is what is there, where is it, where should it be. So then we go to outside. Outside is done with trains like this. You can actually see them riding around the country sometimes. These are special trains. This here is a camera, and they record images. Now the reason that they ride is because they do the switch inspection. They have like 9 cameras, 7 of which point down. And ProRail has these images, these front and back facing images, but until now they haven't really done anything with it. So they thought, okay, well, let's see if we can put them to some use. And we can put them to use. So this is some of the things you encounter if you go out there. Now this one here, there's a little bit of graffiti. We don't see that a lot, but you know, it happens. I especially like this one. You know, the guy who plays this one must have said, okay, I'm not going to think for myself today. This boss man says, put it there. Okay, I don't know, this one is a bit dark, maybe you can see it on the screen, but this is a black sign with yellow text, but it has withered a bit. So even if the picture wasn't as dark as this, you wouldn't be able to see the print. And you know, there's a lot of stuff that can go wrong. And this is just if the image, if the signs are in the right place. Right? They might be there, they might look good, but they might be 100 meters too far back or too early. So there's a lot of things that can go wrong. Now I want to do a little bit experiment on you guys. It's still possible because I'm going to ask you to interpret this image. It's a bit dark, but you can still do it. So I have one question, and the question is there a sign on this photo? You can guess if you like.
Yes.
Yes. Why do you think there is this sign in this photo?
Because of the question.
Yeah, there's something round
It
there.
could have been a trick question. Yeah, there's something round there? This one?
Yeah.
Yeah, that one. Okay, so there's something round there. Any other answers? Any other guesses?
Also, there's a vertical pole and we don't see a sign, so that's an indication of the presence of a sign.
Okay. Okay, so the image was supposed to be bright as day and very clear. I can tell you this is not a sign. This is, well, not the sign I'm looking for. So there's the first trick, right? What sign am I looking for? What's the one I want? So I made this traffic light right here. So a sign is, in this question, it's a traffic light. So part one, you need to know what I'm looking for. You need to know what it looks like. So now you know what it looks like. So is there a sign in this picture? Yeah, facing the back. Okay, so the answer is yes, there is one, but I'm not interested in this one. So no, I'm going to say no to this. So I'm going to be very specific. I want it to be facing me, and I want it to be a traffic light. So is there a sign in this image? Multiple. So this one. But it looks different, right? Yep. So now the answer is yes, because I know this is a sign with this matrix sign below it, but this counts as a sign. So even a simple question as, is there a sign here, is going to be, well, it depends. So you need to be very, very specific. And of course, once you teach a computer to look at these things, you need to be more specific still. So these are seemingly easy questions, but they may not be. So I've got one more. Is there a sign in this image? So some of you say no.
Yes.
You say yes?
Yeah. Yes, I say yes as well.
Okay, so why do you say yes?
Because I think I see one, but I'm not
Yeah. Okay. If you see one, where is it?
sure. On the right side of the track, near the pole.
Here?
Yeah.
Is it this?
Yeah.
Could have been. It's not, but it could have
Oh,
been.
that's what I was thinking. I think.
Yeah. So here, okay, well, let's go back one. Here is obvious because you see it right away. Here, now even if the answer turns out to be no, it's not obvious. You have to look for it because it's not right up front. And even here, if the question was not, is there one, yes or no, maybe I ask, how many are there? Now there's two that you can see right away, but maybe there's some other at the back. So if the question is, how many are there, you have to scan the whole image. Now here, because it's not obvious that there's not one up front, you have to scan the whole image again. And this is exactly what we're going to have the computer do. Because if we just give it an image like this, or no, not like this because there isn't one here, but if we say, there's a sign here, there's a sign here, there's a sign here, you figure it out, it's not going to figure it out. There's too much data. There's too much going on. There's a sign, okay, well, maybe this is a sign, because that's here and that's here as well. You know, there's a lot of things that are constant in these images and a lot of things that change. So you can't just say, you tell me, right? So we're going to do this scanning. So the first thing we do is divide it into these windows. Now, I know that the aspect ratio of the sign is a bit longer than it is wide, so I've made these windows, I've made the grid like that as well. Obviously, most of the times, it won't be aligned to a cell like that. So this is, just to make it a bit more insightful, normally these windows overlap. So you won't go from this one to this one, but you have maybe go there in a couple of steps. And especially in the vertical direction, because this is a tall sign, you have a lot of overlapping windows, but you look at them one by one. And once you've done that, you say, okay, well, maybe it wasn't this big, maybe it was smaller, maybe it was further in the back. So you do the same with a smaller window, and then smaller still. So this is what you call a multi-scale search. And the reason you do this is because now you get to inspect every little bit of detail. You say, well, is this a sign? Is this one? Is this one? Is this one? Is this one? And here I have this nicely cut out image of a sign. And again, it's a bit dark, but you would have seen the red light here, and there would be nothing else. And even if you do it like this, then you say, well, they must all look the same, right? Well, more or less. So this one is very dark. There's a lot of stuff going on in the background. But I have another sign cut out exactly the same way, and this is a lot brighter. I mean, even if you look at this pixel right here, at the top top left of this sign is almost white, and it's completely dark here. So even now, you still cannot just compare pixel values. Even this one has its red light on, this one has two, but here it's almost completely black, and here, well, you can't see it because we interpreted the color so well, but the middle pixels are actually fully white. There's nothing red about it. It's only the halo that is red, and we know that there's overexposure in the middle. So we know, yeah, it's white, but it should be red. We don't even see that it's white. But this kind of variation is still present in all of these images. And now I'm going to switch to a video player right now, because I want to show you one little aspect. If I cut out a whole lot of these images and I compare them like this, right now, you can see what is constant and what changes. And what changes is the background. So, you know, sometimes there's these bars, sometimes there's forest, sometimes there's open sky. There's a lot of stuff going on there, but it's different every time. What is constant is this shape right here, the outline. And what is also constant is that no matter what the color of this sign is, it could be gray, it could be dark, but it is always darker than the surroundings. Well, yeah, it's darker, because sometimes the surroundings is dark, but then the inside is darker still. So if you do it like this, we humans can very efficiently say this is constant and this is not. Now, still the computer needs a little bit of help, but we transform the image. And if you're interested in how this is done exactly, I can tell you more about this later. But what we do is we look at the gradients, because, like I said, the sign is usually darker than its surroundings. In this case, because we do it in different color spaces as well, this is a yellow triangle, and in this case you say, well, the inside is more yellow than its surroundings. And then even if you have a sunset coloring everything red, then still the triangle is more yellow than its surroundings. And this is what these lines sort of represent. And as you can see here, if you follow the outline, these lines always point outwards or inwards, just bidirectional. And here in these cells, well, it's sometimes like this, like this. There's not a real clear picture there. But if you then present a whole lot of these features, so I'm not showing the original images anymore. I do this transformation, and so I only show the gradients in these cells, and then you ask the computer, now, tell me what is constant here, and then it's going to learn. Only then will it figure out that these cells here are important, these ones there are not. They're still important, but for a different reason. And here again, also these cells that are on the edge of the sign, they point outwards. These are actually signs, so out is a different direction than in here in this case. And you can really recognize the triangular shape, and you can, if you know how to interpret it, also see, okay, well, the color is more this, more that. And this is how we can teach a computer to look for constant things, by making them more obvious at first. And if we make them more obvious, then we only need a handful of examples, because, of course, if you take a picture, it's not going to be as pretty cut out as this. So you have to do this by hand the first couple of times. And in this system, I only need to cut out maybe 5 examples, and then say, train it, figure out what is constant about these. Now, look at this hour-long video and tell me where they are. And it's going to give me a whole lot of junk. But among this junk is more training examples. They say, not this one, not this one, not this one, add these, add these, add these, train again. And then you do this 2 times, and then you've got a good detector. So you got very few data, but you get very good results. So this is how it is in action. This is not real time. This is also a bit fast forwarded, because we know there's nothing in that fast forwarded section. Here there is something, and you see these bounding boxes. Those are the actual search windows from the multi-scale search that yielded the result. And what you can also see is that there's multiple detections in time. There's actually multiple detections in space as well. Because if you have this window that says, yes, this is the sign you're looking for, then the one right next to it is going to be yes as well, and yes, so there's a whole bunch of them cobbled together. And you have to filter them, and then you have to make it all nice. And then this is what happens. So, what you now have is which image shows what sign where in the image. But you don't know where it is in the world yet. So, this is where the GPS comes in, and I'm just going to be real quick about this because I'm also running out of time. But every image is coupled with a GPS location. That means every image, I know where that image was taken. I know where the camera was. I don't know where the sign is yet. But what I can do, here's how, this doesn't play either. Okay, well that's it. So we use Google Earth as a debugging tool, but it also would have been very nice to visualize it with this way. But what you can get is if my camera is at this point, and I know where the camera is facing, I know the camera is facing the travel direction, and then the sign was seen to the right of the image. So now I have now a sideline. Right? Oh, I can. I'll put it here so that the remote people can look as well. Yes. So, I have. So, here's the track, and I have a picture taken here. And use all the colors. And at the time I took this picture, I know somewhere along this line was the sign. I know there's a sight line. I don't know where it is because I only have two-dimensional cameras. The images are 2D, so I can guess by the size of the sign where it is. But these things vary, so this doesn't actually work. The only thing I know for sure is it's somewhere along this line. Now here comes the important part because I see it multiple times in a row. So the next image, the train was here, and of course the sign sort of shifts along your view. So now I saw it at this angle, and you can see what's going to happen if you do this a couple of times. And this is really what it looks like in Google Earth. They will all cross where the sign really was. And not only that, you actually know how it goes horizontally, but also vertically. So you also know this thing is at 3 meters height. So now by triangulation, I have determined that here is the thing I'm looking for. I now have what it is and where it is. Likewise, the OBE sheets has what it is and where it is. And now you can do a direct comparison. And this is how the two data sources come together. And this is basically also the end of the talk. So now there's time for questions. If there are any. Yeah.
So, two questions. One is, so you're scaling the windows on every frame.
Mm-hmm.
You also rotate the grid to recognize the fallen over ones, or
No.
you just skip those?
Yeah, you want to skip those.
Yeah.
Because exactly, because here, because I haven't really talked about this, but of course the construction plans and how it really is. Now here there's a table, and it shows all of that now because this is a development version, but the color of this line says this thing inside was matched with that thing outside. Now this green line means we've seen it and we've seen it. So it's one of these signs here, and it's exactly this sign right here. But if there's a red one, and can I zoom in on this? Probably not. But the red line means we saw something inside that we didn't match with anything outside, or vice versa. So the fallen over one, you want to miss it, and then you click on this, and you go to the construction plan, you say, this thing has not been seen. And then the video also goes to where you would have expected to see it, and then you can see, it's fallen over. And then, of course, this system will only sort of dig up the discrepancies, but the measures need to be made by hand. So somebody has to look at it and say, well, it actually is there, but the light was wrong, or it has fallen over. We need to fix this. So the measures need to be specified by humans.
My other question was, what kind of system do you need to do this kind of processing? Do you do development just on your MacBook, or do you have a server for this to run the actual computation or something?
Yeah, so the hardware this runs on, it runs on anything, but the more cores you have, the faster it will run. Most computer vision tasks are very suitable for parallelization, and so my workbook has, I think, 4, maybe 8 cores if you count hyperthreading, and it works, but it's kind of slow. So we bought a machine specifically to do this processing, and it has 32 cores, and they're all being used to about 98% or so. So that's a lot of heat coming from that machine, but it can do it near real time. If we should have made it suitable for GPU as well, we probably should have gone even faster. But we wanted this to be deployable everywhere. So have a machine, you can run the software. You don't have a GPU, no problem, we can run the software. And we thought that would be easier to put it in the cloud. And then later we found out you can rent clouds that have GPUs as well. So we might as well have put it on the GPU. We didn't, but it's still, the more cores you have, the faster it will go. Yeah.
Can you give an indication of how well it worked?
Pretty damn good. Okay, so at this point we have there's always a trade-off between do I detect some things that aren't the thing that I'm looking for, but they look similar, or do I miss them altogether? And for this project, it is essential that you do not miss anything. That means if there's there's one example. We have green-blue sign, triangular, point up, and it turns out that this pattern is actually very common in clouds as well, because then you have a couple of clouds, and then the middle is where the sky shows through, and then you have a triangle, point up, and it's about the right color. It's more blue than the surroundings. So these are false positives, and these we can filter out because of the triangulation. We actually do know, well, this thing is about 50 kilometers up in the air. So these are easy to filter. But a lot of these smaller signs, especially all the traffic light type of things, they have this number on them. And those are yellow signs with, actually there's yellow text and a black sign. But the detector reacts to, okay, something rectangular and yellow. But there's a lot of stuff that's rectangular and yellow. They're called trains. And we have a lot of false positives, but we're sort of, okay, well, we cannot make the detector more scrupulous or more strict, because then you might miss the actual numbers. So there are a couple of more improvements that we would like to do if there's time. So right now, it really depends on the type of asset you're checking. Those triangular ones, the yellow ones, they're spot on. We never make any mistakes against those. The traffic light signs, we never make any mistakes against those either. The ones that are up the clouds, well, the cloud ones are the most common mistakes, but we can filter them out. So it depends on which asset you're looking for, whether it works well enough or not. One guideline is so the smaller they are, the harder they are to detect. 3 questions. You go first.
You showed a vandalized sign in the side with some graffiti on it.
Yep.
Does it recognize a sign as big? Well, there is a sign, but it's not in the proper state?
Not really. So if there's vandalism, if it's really clobbered up the whole sign, then this will cause the sign not to be detected, which is good because you can't see the sign and it will show up as a red line, and you say, okay, go clean that. If there's only a little bit of graffiti on it, then it's not going to be bothered by it, and it said, okay, I found it, we're good. Another thing though is that with the detection, it's not yes or no, it's actually a score. So the higher the score is, the more confident you can be that it is there and it looks all right. It's not a one-on-one mapping, because sometimes you see this really beautiful sign and it has a low score. But what you can do is okay, even if everything is green across the board, show me the lowest scoring ones, just as a sort of browsing through them, and then you might find out the vandalized ones like that.
Okay.
Yeah. You had a question?
So do you train the system? Does it get better?
It can get better because every time you have a detection, and especially if it's matched, right? What you can do is have the analyst go through it and sort of confirm it. So yeah, you saw it, it's all right. And then the score comes into play again, because the lower the score was, the more trouble the system had with it. So if an analyst confirms, yes, this is one, you can put it in the training set. Likewise, if there's a red one here, so there was a detection somewhere, and the analyst looks at it and say, yeah, but this was a false positive. Well, you get more training data. So the mechanism is in place, but we're not actually using it at the moment. We don't really need to, because after the initial training, these detectors are pretty good. But we do have the mechanism in place, and if the customer wants it, we can spend some time and build it.
And share between the different systems that run
Yeah.
it.
Yeah. Exactly. You need this feedback.
So it's possible with what you already built to.
Yeah, it's completely ready for feedback and getting better and retraining. Except that the mechanism is a little bit involved, because from the GUI you need information back to the start of the chain. So there's some work that needs to be done, but the trainer is ready for it. The cutouts, they're all ready to go. Yeah. Any more? You had a question?
Thanks for the talk. It's very interesting. I have a question. You talked about the systems you're using, but can you tell me more about the frameworks you're using to I think we're doing SIFT for the skill, for the recognition, the feature recognition. Are you doing something for this?
Yeah, we're using OpenCV. It's not SIFT, it's actually HOG, like a histogram of oriented gradients. Yeah. And because the original HOG does not use color information, so I made this extension on it. I do it in 3 color channels independently. It's not RGB, because I took some literature and said, okay, what is the best color space to use for this? Turns out to be YUV. So the Y is like the luminance. So if you have black and white TV, that's all Y. And this might be nice, because I showed you here. So this is the Y channel, and here the gradients are unsigned. That means left or right is the same, it's horizontal. Up or down, same, vertical. So for the luminous channel, this is actually the best way to go. This is either the U or the V channel, I don't know, but those contain color information. Here the gradient is important, because now this has to be more yellow than the surroundings, not the other way around. The reason why I don't use the sign gradients here is because, okay, well, this may be an extreme example, but we have white signs as well. And then you say, okay, well, a white sign, that's always brighter than its surroundings, right? And this turns out to be wrong, because there's always situations where there's a big shadow on your white sign and it's against this overexposed sky, and then you'll miss it completely. And somehow this never happens in the color channels, but it does very regularly happen in the luminous channel. So this one is unsigned and the color channels are signed.
1 year or 2 ago, I saw a presentation by NVIDIA who did a similar work for detecting people, signs for driverless cars.
Yeah.
Are you using a similar technique, or is it radically different?
It's basically the same, because these HOG features, if you look at the literature, they usually when there's a new technique, there's one demo application that the original authors provide, and then everybody else uses it for just that, and nobody expands, because this is a general framework. But So pedestrian detection is actually the demo application that I think the original authors were Dalal and Triggs. That was the example they provided, and everybody's been using hard features to do pedestrian detection since. Probably NVIDIA is still doing that. So yes, we're using the exact same system, except I do the color extension. For traffic science, this is a sensible thing to do. For pedestrians, this is not, because everybody has different colors. And this is actually why the original implementation didn't have any color information. They didn't use it. So, yeah.
Okay, thanks.
Een mooie kleur hebt gebruikt voor